Exoplanets are worlds that circle stars beyond our Sunday. Astronomers detect them using methods like the transit technique, where a planet passes in front of its star and blocks some light, or the radial velocity method, which tracks small wobbles in a star caused by a planet's gravity. These planets come in many forms. Some are gas giants, like Jupiter, but orbit very close to their stars, while others are rocky and may resemble Earth. For example, Kepler-186f is about the size of Earth and lies in the habitable zone of its star, where liquid water could exist. Not all exoplanets are alike. Some orbit two stars. Others circle faint red dwarfs. Because they are far away, scientists study their atmospheres by analyzing starlight that passes through them. This research can reveal gases such as water vapor or methane. Imagine looking up and finding a world with thick clouds, strong winds, or even oceans under an alien sky. The search for exoplanets helps us understand how planets form and whether life might exist elsewhere. Each discovery adds to a growing picture of a universe full of diverse and surprising worlds. In 1992, astronomers Alexander Wulzan and Dale Frail confirmed the first exoplanets. They found them orbiting a pulsar, which is the dense, spinning core left after a massive star explodes. These planets, now called PSR B 1257 plus 12b and c, surprise scientists because no one expected worlds to form or survive around such a harsh remnant. The discovery showed that planets could exist in places once thought impossible. Before this, many suspected exoplanets might be real, but evidence was weak or uncertain. The 1992 finding was different because the signals from the pulsar were so precise that even tiny variations could be measured, leaving no doubt. Imagine the pulses of the star acting like a clock, and the planets causing slight delays, like someone nudging the hands of a watch. That is how their presence became clear. This breakthrough opened the door to modern exoplanet science, leading to thousands of later discoveries around stars of all types. What began with two small, unexpected planets around a dead star turned into a field that now explores giant gas planets, rocky Earth, like ones, and many strange worlds across the galaxy. PSR B 1257 plus 12b is one of the first exoplanets confirmed found orbiting the pulsar PSR B 1257 plus 12, about 2,300 light-years from Earth. It is much smaller than Earth, with a mass only a few times greater than our Moon. Because it circles a pulsar, the environment is extreme, with high radiation levels and little chance for life as we know it. The planet was detected when tiny changes in the timing of the pulsar's radio pulses revealed its pull on the star. Those changes acted like fingerprints, proving the planet's existence. Along with PSR B 1257 plus 12c and d, it forms a small planetary system that surprised astronomers by showing that planets can survive or even form after a star explodes. Imagine a dead star spinning like a lighthouse, while small worlds keep orbiting in its beam. Although PSR B 1257 plus 12b is not a place for habitability, its discovery was historic. It proved planets exist outside our solar system, sparking a wave of searches that later found more than 5,000 exoplanets of many different kinds. This small, hostile world remains a milestone in astronomy's effort to map planets across the galaxy. Exoplanets are located within the Milky Way, which is the galaxy that also contains our solar system. Most known exoplanets lie within a few thousand light-years of Earth, since current telescopes cannot yet detect planets in more distant parts of the galaxy. Astronomers often find them near stars in the galactic disk, where stars like the Sunday are most common. For example, the Kepler Space Telescope discovered thousands of exoplanets by staring at one small patch of the Milky Way. This shows that planets are widespread and likely orbit many of the billions of stars in the galaxy. Some exoplanets are hot gas giants that circle very close to their stars, while others are small rocky worlds. A famous example is the TRAPPIST-1 system, about 40 light-years away, which has 7 Earth-sized planets orbiting a cool red dwarf star. Because light travels at a fixed speed, when astronomers study exoplanets, they are also looking back in time, observing the light that left those systems years or centuries ago. Imagine standing on Earth and knowing that around distant stars, unseen worlds circle, each with conditions shaped by their sun, size, and orbit. The Milky Way holds a vast range of these hidden planets. Most exoplanets discovered so far lie within a few thousand light-years of Earth. This is not because planets beyond that range do not exist, but because our instruments cannot detect them at greater distances. Telescopes like Kepler and TESS focus on nearby stars within the Milky Way, where the faint dips in starlight caused by planets are still measurable. For example, Kepler-452b, often called a super-Earth, is about 1,400 light-years away, and TRAPPIST-1's planets are only 40 light-years away. These distances sound large, but they are tiny compared to the Milky Way's size of about 100,000 light-years across. Detection methods such as the transit technique or radial velocity require clear signals which fade with distance. Imagine trying to hear a whisper across a room versus across a stadium. The further away the star, the weaker the planetary signal becomes. As technology improves, astronomers may be able to detect planets much farther out, including in different regions of the galaxy. For now, the catalogue of known exoplanets forms a local sample around Earth, showing us a diverse set of worlds, but only within a small neighborhood of our galaxy. As of 2025, astronomers have confirmed more than 5,600 exoplanets. Each one orbits a star beyond our Sunday, and together they reveal how common planets are in the Milky Way. These confirmed worlds come from years of data collected by missions such as Kepler, TESS, and ground-based observatories. They range from giant gas planets larger than Jupiter to small rocky ones close in size to Earth. For example, Kepler identified thousands of candidates, many of which were later confirmed through follow-up observations. TESS continues this work by scanning almost the entire sky for new transits. The number also reflects improved methods of confirmation. The transit technique, where a planet blocks part of its star's light, and the radial velocity method, which detects a star's wobble, remain central tools. In some cases, astronomers use direct imaging or gravitational microlensing to detect planets in more distant systems. Imagine a growing catalogue, where each entry is a world with its own orbit, size, and temperature. While 5,600 planets is a large number, it represents only a fraction of what exists. The Milky Way contains billions of stars, and most likely billions of planets waiting to be found. Thousands of exoplanets remain in the candidate stage, waiting for confirmation. These are detections that show strong signals of being planets, but need further checks to rule out other explanations, such as binary star systems or instrument noise. The Kepler mission produced the largest set of candidates, with more than 2,000 still under review. TESS also continues to add new signals that appear to be planets, but astronomers must confirm them through follow-up observations using ground-based telescopes or other space missions. Confirmation often requires more than one method. For example, a transit signal can suggest a planet, but measuring the star's radial velocity helps confirm its mass. This prevents mistakes since other events, like star spots or stellar activity, can mimic a transit. Imagine spotting a faint shadow and needing to double-check if it comes from a planet or something else moving in front of the star. Candidates serve as a vital pool for discovery, showing where to focus limited telescope time. Many of today's confirmed exoplanets started as candidates years earlier, and with steady observation, the list of confirmed worlds continues to grow while new candidates keep appearing. Exoplanets come in a wide range of sizes, from worlds smaller than Earth to giants larger than Jupiter. Some, called sub-Earths, are rocky and may be only half the size of our planet, making them difficult to detect because they block so little starlight. Others, known as super-Earths, are 2 to 10 times Earth's mass and often have thick atmospheres or deep oceans. These planets do not exist in our solar system, but are common around other stars. On the larger end, gas giants called hot Jupiters orbit, close to their stars, and can be several times bigger than Jupiter. For example, Washington SPI -17. b is nearly twice Jupiter's size, and orbits so close to its star that a year there lasts only a few days. Between these extremes are Neptune-sized planets, with thick atmospheres of hydrogen and helium and no solid surface. Imagine a lineup where a small rocky planet the size of Mars stands next to a super-Earth, with crushing gravity followed by a gas giant that dwarfs Jupiter. The diversity shows that planets form in many ways, producing sizes and structures unlike those in our own solar system. Exoplanets circle many kinds of stars, each creating different conditions for the planets that orbit them. Red dwarfs, the most common stars in the Milky Way, are small and cool, so their habitable zones lie very close in. The TRAPPIST-1 system is an example, with 7 Earth-sized planets packed tightly around a faint red dwarf. Sunday-like stars, known as G-type stars, host planets in more familiar conditions. Kepler -452b, sometimes called Earth's cousin, orbits a star much like the Sunday. These systems are easier to compare with our own because their light and temperature resemble what we experience on Earth. Giant stars, however, they are evolved stars that have expanded late in their lives, and planets around them often orbit farther away or risk being engulfed as the star grows. Some giant stars still hold planets, showing that worlds can survive dramatic changes in their host star. Imagine 3 different skies, one dim and red from a dwarf, one bright and yellow like our Sunday, and one enormous and swollen from a giant star. Each type of host star shapes the orbit, temperature, and long-term fate of its planets. Some exoplanets orbit more than one star, creating systems unlike our own. These are called circumbinary planets, when a single planet circles 2 stars at once. An example is Kepler -16b, which orbits a pair of stars about 200 light-years away. To someone standing there, 2 suns would rise and set, casting shifting patterns of light and shadow across the surface. Other planets may belong to more complex systems with 3 or even 4 stars. In these cases, the orbits can be stable if the stars are close together and the planet circles from a distance, or if the stars are far apart and the planet orbits only one of them. Stability depends on how the gravity of each star interacts, which astronomers test using models and long-term observations. These multi-star systems show how flexible planet formation can be. Imagine building a planet while 2 stars tug in different directions, yet the planet still holds an orbit. While less common than planets around single stars, circumbinary planets prove that nature can form worlds under a wide range of conditions, even in the glow of more than one sun. The transit method is one of the main ways astronomers detect exoplanets. When a planet passes in front of its star from our point of view, it blocks a small fraction of the star's light. This causes a dip in brightness that telescopes can measure with high precision. The dip repeats at regular intervals if the planet has a stable orbit, confirming that it is not just a random change in the star's light. The depth of the dip reveals the planet's size, while the time between dips shows its orbital period. For example, if a star's light dims by 1% every 10 days, Astronomers can estimate both the planet's size and its distance from the star. Missions such as Kepler and TESS rely on this method, scanning thousands of stars at once to look for repeating dimming patterns. Imagine staring at a street lamp and noticing a moth fly across it. Each time the moth passes, the light flickers in the same way, letting you know something is crossing in front. The transit method works on the same principle, turning tiny flickers of starlight into evidence of planets far beyond our solar system. The radial velocity method detects exoplanets by measuring how a star wobbles under a planet's gravitational pull. As a planet orbits, its gravity tugs the star, causing it to move slightly toward and away from Earth. This motion shifts the star's light through the Doppler effect. Wavelengths stretch when the star moves away and compress when it moves closer. Sensitive spectrographs can record these shifts with great accuracy. The size of the wobble reveals the planet's mass, while the period of the wobble gives its orbital distance. For example, a massive planet like Jupiter creates a larger wobble than a smaller Earth. Like planet, early exoplanet discoveries, such as 51 Pegasi b in 1995, used this method, proving that planets could be found around normal stars. Imagine holding a heavy ball on a string and swinging it in a circle. While the ball moves widely, your hand also shifts slightly in response. The same happens between a planet and its star. The radial velocity method remains a key tool, often used alongside the transit method, to confirm planets and provide details about their true size and mass. Direct imaging is a method that captures real pictures of exoplanets by separating a planet's faint light from the overwhelming glare of its star. Because stars shine billions of times brighter than their planets, astronomers use special instruments called coronagraphs or star shades to block the starlight. This allows the planet's reflected or emitted light to become visible. The technique works best for young, massive planets that glow in infrared and orbit far from their stars, where the glare is easier to reduce. For example, images of planets around the star HR 8799 show several gas giants orbiting at wide distances, like a family portrait of another solar system. Direct imaging not only proves the planets exist, but also lets scientists analyze their atmospheres by studying the spectrum of the captured light. This can reveal gases like methane or water vapor. Imagine trying to see a firefly hovering next to a lighthouse beam from miles away. You need to block the beam to spot the faint glow. Direct imaging is challenging but powerful, offering rare glimpses of alien worlds as actual points of light against the darkness of space. Gravitational microlensing finds exoplanets by using the way gravity bends light. When a star passes in front of a more distant star, its gravity acts like a lens, magnifying the background star's light. If the closer star has a planet, that planet adds a smaller distinct signal to the light curve. Astronomers can detect this signal even if the planet orbits far from its star, something other methods often miss. Microlensing can reveal planets as small as Earth and even free, floating planets not bound to any star. For example, in 2004 scientists detected a planet several times the mass of Jupiter using this method, even though the system was thousands of light years away. The effect is rare and unpredictable, so astronomers monitor millions of stars, waiting for alignments to occur. Imagine two flashlights lined up. With one closer to you, the nearer light bends and brightens the farther one. If a pebble hangs near the closer flashlight, you would see a brief extra flicker. Gravitational microlensing works in the same way, turning cosmic alignments into a tool for spotting hidden planets across the galaxy. Timing variations detect planets by tracking small changes in regular signals from stars. In pulsar systems, the star emits radio pulses as steady as a clock. If a planet orbits the pulsar, its gravity tugs the star, causing tiny shifts in the arrival time of those pulses. This is how the first confirmed exoplanets were discovered in 1992 around pulsar PSR B1257+12. The method also works with eclipsing binaries, where two stars pass in front of each other from our point of view. Their eclipses follow a precise schedule, but if a planet orbits the pair, its pull can slightly speed up or delay the timing of those eclipses. Measuring these shifts reveals the presence and mass of the planet. Imagine watching a metronome tick back and forth with perfect rhythm. If a small weight attaches to it, the ticks come a little earlier or later, showing that something is disturbing the motion. Timing variations rely on this principle, turning predictable cosmic rhythms into sensitive detectors of planets that might otherwise remain hidden. This method is rare but powerful, especially for finding worlds in unusual or extreme systems. Most exoplanets have been discovered using the transit method, which detects small dips in a star's brightness when a planet passes in front of it. Missions like Kepler and TESS rely on this technique because it allows astronomers to monitor thousands of stars at once and catch many planets with repeating signals. Kepler alone identified over 2,000 confirmed planets and thousands more candidates by staring at one small region of the Milky Way for years. The method works best for planets with orbits lined up so that transits are visible from Earth. While this alignment is rare, surveying large numbers of stars makes detections common. The transit method also provides details beyond discovery. The depth of the dip reveals the planet's size, and by combining transit data with radial velocity measurements, astronomers can determine density and composition. For example, a shallow dip might mean a planet smaller than Earth, while a deeper one could signal a giant like Jupiter. Imagine tracking a street lamp and noticing regular flickers caused by something crossing in front of it. By watching many lamps at once, you catch many flickers. This simple approach explains why the transit method dominates exoplanet discoveries. NASA's Kepler Space Telescope transformed the search for exoplanets by using the transit method on an unprecedented scale. Launched in 2009, Kepler observed a fixed patch of sky for nearly a decade, monitoring the brightness of about 150,000 stars. By recording tiny dips in light as planets crossed their stars, it revealed thousands of planets and showed that planets are common in the Milky Way. Among its findings were Earth-sized planets in the habitable zones of their stars, such as Kepler-186f. The mission also uncovered a wide variety of worlds, including hot Jupiters, super-Earths, and compact multi-planet systems. Kepler's precise and continuous data set, the foundation for modern exoplanet science, shifting the question from whether planets exist outside our solar system to how many and what kinds there are. Imagine staring at a single crowded field of stars for years and catching thousands of faint repeated flickers, each marking a new world. Even after its retirement in 2018, the data Kepler collected continues to produce discoveries as astronomers reanalyze its vast archive. Its success paved the way for newer missions like TESS, which now scans almost the entire sky using the same approach. TESS, the Transiting Exoplanet Survey satellite, launched in 2018 to expand on Kepler's success. Instead of focusing on one patch of sky, TESS scans nearly the entire sky, dividing it into sectors and observing each for about a month. This approach allows it to monitor millions of stars, especially bright and nearby ones that are easier to study with ground-based telescopes. TESS looks for the same signature as Kepler, regular dips in brightness caused by planets passing in front of their stars. Because it targets closer stars, the planets it finds are prime candidates for detailed follow-up. For example, astronomers can use the James Webb Space Telescope to analyze the atmospheres of test planets, searching for gases like water vapor or carbon dioxide. TESS has already discovered hundreds of confirmed exoplanets, with thousands more candidates awaiting confirmation. Among its finds are small rocky planets in the habitable zones of red dwarfs, systems where multiple planets transit, and gas giants that orbit close to their stars. Imagine TESS as a surveyor mapping the neighborhood, flagging promising targets for closer inspection. Its wide coverage ensures that many of the worlds it identifies can be studied in detail by current and future instruments. Radial velocity was the first method to confirm a planet around a normal star. In 1995, astronomers Michel Mayor and Didier Queloz used it to discover 51 Pegasi b, a gas giant orbiting very close to its star. The technique works by measuring the star's wobble caused by the gravity of an orbiting planet. As the star moves slightly toward and away from Earth, its light shifts due to the Doppler effect. Sensitive spectrographs can detect these shifts even when the motion is only a few meters per second. The size of the wobble reveals the planet's minimum mass, while the period of the wobble gives the orbital distance. This method proved that planets exist around stars like our Sunday, changing astronomy overnight. For example, 51 Pegasi b turned out to be a hot Jupiter, a giant planet orbiting in just 4 days. Something no one expected. Imagine watching a person on a swing push a much larger friend. Even though the friend barely moves, the motion still gives away the push. Radial velocity works on the same principle, showing planets through the gentle but measurable pull they exert on their stars. Direct imaging of exoplanets is rare because stars are so much brighter than their planets. But advances in technology are making it more common. Instruments now use coronagraphs to block starlight or star shades to separate the faint glow of a planet. Large ground-based observatories, such as the Very Large Telescope and space telescopes, like the upcoming Nancy Grace Roman Space Telescope, are designed to improve this technique. Direct imaging works best for young, massive planets that still give off heat and orbit far from their stars. For example, astronomers have captured images of multiple gas giants around the star HR 8799, creating the first direct family portrait of another planetary system. The method is valuable because it allows scientists to study a planet's light directly, breaking it into spectra to identify gases in its atmosphere. Imagine trying to see a candle flame next to a searchlight. New instruments act like shields, letting the faint flame come into view. While only a few dozen exoplanets have been directly imaged so far, the steady progress of telescopes promises clearer and more detailed views of distant worlds in the near future. Hot Jupiters are gas giants that orbit extremely close to their stars, often within a few million miles. Unlike Jupiter in our solar system, which orbits far from the Sun, these planets complete a year in only a few days. Their close orbits expose them to intense radiation, heating their atmospheres to thousands of degrees. Many hot Jupiters are larger and puffier than Jupiter, with gases expanding under the star's heat. The first exoplanet found around a Sunday, like star 51 Pegasi b, is a hot Jupiter, discovered in 1995 using radial velocity. These planets are easier to detect because their large size and short orbits create strong signals. For example, their transits cause deep dips in starlight, and their gravity produces noticeable wobbles in their stars. Astronomers have also observed atmospheric details, such as sodium and water vapor, by studying starlight filtering through them. Imagine a world of swirling clouds and blistering winds orbiting so near its star that the sky glows with permanent daylight. While they are unlikely to host life, hot Jupiters reveal much about how planets form and migrate. Their strange locations challenge earlier models that expected gas giants only in distant, colder orbits. Super-Earths are planets larger than Earth but smaller than Neptune, with masses up to 10 times greater than Earth's. Despite the name, they do not need to resemble Earth in climate or habitability. Some may be rocky worlds with strong gravity, while others could have thick atmospheres that make them more like mini-gas planets. Many super-Earths orbit closer to their stars than Earth does to the Sun, creating hot, dense environments. For example, Kepler-22b is considered a super-Earth in the habitable zone, though its true nature, rocky or gaseous, remains uncertain. Their diversity makes them intriguing to scientists, especially because none exist in our solar system. Super-Earths are common in the galaxy, and their size makes them easier to detect than smaller Earth. Like planets, imagine walking on such a planet where gravity might be twice as strong as on Earth, making every step heavier. Their thick atmospheres could trap heat, while others might have volcanic activity powered by their mass. These planets expand our understanding of planetary types, showing that solar systems often form worlds very different from those we know. They remain prime targets for studying conditions that may support liquid water and possibly life. Mini-Neptunes are planets smaller than Neptune, but larger than Earth, often with thick atmospheres of hydrogen, helium, or water vapor. They may also have icy layers or deep oceans beneath their clouds. Their size range usually falls between 2 and 4 times Earth's diameter. These planets are unlike anything in our solar system, sitting between rocky super-Earths and gas giants. For example, Kepler-138d is a mini-Neptune, about 1.5 times Earth's size, with a likely water-rich composition. Their thick atmospheres make them challenging places for life as we know it, since surface conditions could be extremely hot, high pressure, or completely hidden under deep clouds. However, mini-Neptunes are important because they show how planets can form with both solid cores and gas envelopes, straddling the line between rocky and gaseous worlds. Imagine standing on a small probe as it sinks into such a planet's atmosphere, pressure rising, light dimming, and layers of vapor becoming denser, until no surface can be seen. Many mini-Neptunes orbit close to their stars, where heat causes their atmospheres to expand and escape into space. Their variety makes them valuable for testing theories about planetary formation and evolution across the galaxy. Terrestrial exoplanets are rocky worlds, similar in structure to Earth, with solid surfaces made of rock and metal. They can range in size from smaller than Mercury to a few times larger than Earth, because they resemble the planets we know best. They are prime targets in the search for habitable environments. For example, Proxima Centauri b is a terrestrial planet orbiting in the habitable zone of the closest star to our Sun. Another system, TRAPPIST-1, contains 7 Earth-sized rocky planets, 3 of which lie where liquid water could exist. Terrestrial exoplanets vary widely in conditions. Some may be scorched by intense starlight, with molten surfaces, while others may be frozen wastelands, orbiting dim red dwarfs. Imagine standing on one with mountains, valleys, and perhaps oceans under an alien sky. The ground firm underfoot, unlike the gaseous layers of a giant planet. Detection of these worlds is difficult because their small size produces faint signals. Yet they are the most exciting type when searching for life. Since Earth is our model for a living planet, they show that rocky worlds are not unique to our solar system, but widespread across the galaxy. Water worlds are exoplanets, thought to be covered in global oceans, with little or no land. They may form with high amounts of ice and water, which under the right conditions melt into deep seas. Some may resemble giant versions of Earth's oceans, while others could have layers of ice over liquid water kept warm by pressure and internal heat. For example, Kepler-22b and GJ1214b are possible water-rich worlds, though their exact nature is still debated. These planets may have atmospheres thick with steam, and their surfaces hidden beneath endless oceans stretching across the globe. Imagine floating on a boat there, with no continents in sight, only waves under a strange coloured sky. Pressure at the ocean depths could be extreme, creating exotic forms of ice unseen on Earth. Water worlds are especially interesting because water is essential for life as we know it. Their study combines astronomy with ocean science, raising questions about whether life could evolve in such vast alien seas. They expand the range of habitable environments beyond rocky land masses, showing that some planets may support life beneath deep oceans. Far different from the landscapes we know, some exoplanets are tidally locked, meaning one side always faces their star, while the other remains in darkness. This happens when the planet's rotation matches its orbit, much like the Moon always shows the same face to Earth. The star-facing side is heated constantly, often to extreme temperatures, while the far side can be frozen. The boundary between light and dark, called the terminator, may be the only region with moderate conditions. For example, many planets orbiting close to red dwarfs are likely tidally locked because their orbits are short and their stars exert strong gravitational forces. Imagine standing on such a planet with a blazing sun fixed in one spot in the sky, never moving, while the other side of the world lies under eternal night. The contrast creates powerful winds and storms as heat flows from the hot side to the cold side. Some models suggest that atmospheres or oceans, if present, could help redistribute heat, making life possible along the twilight band. Tidally locked planets challenge our understanding of habitability, showing that even worlds with extreme conditions may still hold stable regions where water and life could exist. Rogue planets are worlds that drift through space without orbiting a star. They may have been ejected from their original systems by gravitational encounters or formed in isolation. Without a star's light, these planets are cold and dark, warmed only by internal heat or radioactive decay in their cores. Estimates suggest there could be billions of rogue planets in the Milky Way, making them as common as stars. Some may be gas giants like Jupiter, while others could be rocky Earth-sized planets. Imagine a lonely world floating in interstellar space, its surface shrouded in ice, with no sunrise or sunset. Despite the cold, some theories suggest that underground oceans could exist, insulated beneath thick layers of ice, providing potential habitats for life. Rogue planets are difficult to detect because they do not reflect starlight, but astronomers can spot them using gravitational microlensing when they pass in front of distant stars. Each detection adds to the picture of a galaxy filled not only with star-bound planets but also with these wanderers. Their existence shows that planets are not always tied to stars, and that planetary formation can lead to solitary paths. Lava worlds are exoplanets, so close to their stars that their surfaces are molten. The intense heat vaporizes rock, creating oceans of lava and atmospheres filled with metal vapors. These planets orbit in just hours or days, leaving them scorched by constant stellar radiation. An example is Kepler-10b, a rocky planet with temperatures hot enough to melt iron lava worlds. May also experience extreme volcanic activity, with eruptions feeding their glowing atmospheres. Imagine standing on such a planet where the ground shifts like a sea of molten rock, and the air glows from the heat. On the night side, temperatures could drop sharply, causing rock vapors to condense and rain down as minerals. These worlds provide a glimpse of what young Earth may have looked like billions of years ago when its surface was still molten after formation. Studying them helps scientists understand how rocky planets evolve under extreme conditions. Though hostile to life, lava worlds are valuable for testing models of planetary geology and atmospheres. Their fiery surfaces highlight the extremes that exist in planetary systems, showing that not all rocky worlds are stable or Earth-like. Ultra-hot Jupiters are gas giants, orbiting so close to their stars that their temperatures exceed 2,000 degrees Celsius. At these extremes, molecules in their atmospheres break apart, leaving clouds of atomic hydrogen, iron, and other metals. Their short orbits, often less than 2 days long, expose them to constant stellar radiation. For example, Washington SP-121b is an ultra-hot Jupiter with an atmosphere hot enough to vaporize metals, which may then escape into space. These planets often show strong winds, carrying vaporized elements from the day side to the cooler night side, where they condense. Imagine a world where droplets of iron or silicate rain fall from superheated skies. Their size and extreme conditions make them easier to detect, as they create deep transit signals and strong radial velocity effects. Studying them reveals how atmospheres behave under conditions far beyond those found in our solar system. While they are unlikely to host life, ultra-hot Jupiters serve as laboratories for testing physics in extreme environments, helping astronomers refine models of atmospheric chemistry and heat transfer. Their blazing skies show how diverse planetary conditions can be across the galaxy. Ice giants are exoplanets, similar in size and composition to Neptune or Uranus, with thick atmospheres over icy rocky cores. They form beyond the snow line of their systems, where temperatures are low enough for water, ammonia, and methane to freeze during planetary formation. Their atmospheres are dominated by hydrogen, helium, and icy compounds, giving them bluish appearances in our solar system. Many detected exoplanets fall into this category, often with masses between Earth and Jupiter but smaller than gas giants. Imagine a cold world with layers of clouds, fierce winds, and possibly subsurface oceans beneath icy mantles. Ice giants play an important role in shaping planetary systems, as their gravity can influence the orbits of smaller planets and comets. They may also migrate inward, altering system dynamics. Exoplanet examples include several Neptune-like worlds found by Kepler, some orbiting surprisingly close to their stars. Studying these planets helps scientists understand both the origins of our own ice giants and how common they are elsewhere. Their icy compositions expand the diversity of known planet types, showing that worlds with deep frozen chemistry are widespread across the Milky Way. 51 Pegasi b was the first confirmed exoplanet discovered around a Sunday. Like star in 1995, astronomers Michel Mayor and Didier Queloz detected it using the radial velocity method, which revealed the wobble of the star caused by the planet's gravity. The discovery shocked scientists because the planet turned out to be a hot Jupiter, a gas giant, orbiting extremely close to its star. It completes a year in about 4 days. Unlike Jupiter's 12-year orbit, its atmosphere is superheated, and conditions there are hostile, with temperatures high enough to strip gases into space. Imagine a giant world racing around its star so quickly that its sky never changes, locked in perpetual daylight on one side. 51 Pegasi b proved that planetary systems could be very different from our own, overturning earlier models that expected gas giants only in distant, cold orbits. This single detection opened the floodgates for exoplanet science, showing that planets could be found with precise measurements and inspiring new surveys that later discovered thousands more. The planet remains a landmark in astronomy, remembered as the first step toward proving that worlds beyond our solar system are real and diverse. Kepler-22b is an exoplanet discovered in 2011 by NASA's Kepler Space Telescope. It orbits in the habitable zone of its star, a region where temperatures could allow liquid water on a planet's surface, about 600 light-years from Earth. It was the first confirmed planet in a Sunday, like star's habitable zone, making it a major milestone. Kepler-22b is about 2.4 times Earth's diameter, placing it in the super-Earth category. Its mass and composition remain uncertain, so it may be rocky, ocean-covered, or more like a mini Neptune with a thick atmosphere. Imagine looking up at its sky. The star is slightly cooler than our Sunday, but the planet's orbit keeps it warm enough for water to exist if the right conditions are present. Scientists cannot yet say if it has continents, oceans, or clouds. but its location in the habitable zone makes it one of the most intriguing worlds found so far. Kepler-22b represents the type of target that future telescopes will study more closely, searching for clues about its atmosphere and potential for life. It stands as a reminder that Earth-like conditions may not be rare in the galaxy. Kepler-186f is an Earth-sized exoplanet, located about 500 light-years away. It was discovered in 2014 by the Kepler Space Telescope and is notable for orbiting in the habitable zone of its red dwarf star. The planet is only about 10% larger than Earth, making it one of the closest matches in size. Its orbital period is 130 days, and because its star is cooler and dimmer than the Sunday, Kepler-186f receives a similar amount of light as Earth. This places it in a zone where liquid water could exist on its surface depending on its atmosphere. Imagine standing there under a faint reddish sky, with sunlight dimmer, but steady, warming the planet enough to sustain possible oceans or ice. Scientists do not know its exact composition, but its size suggests it is rocky. The discovery of Kepler-186f was important because it showed that small Earth-like planets can orbit in the habitable zones of common red dwarf stars. It expanded the search for potentially habitable worlds, proving that Earth-sized planets are not unique. Kepler-186f remains one of the most exciting examples in the ongoing hunt for life-friendly exoplanets. Proxima Centauri b is the closest known exoplanet to Earth, orbiting the star Proxima Centauri, which is only 4.2 light-years away. Discovered in 2016 using the radial velocity method, it is at least 1.3 times the mass of Earth. The planet orbits within the habitable zone of its red dwarf star, where surface temperatures could allow liquid water. Its year lasts just 11 days because it circles so close to its star. Proxima Centauri is a flare star, meaning it produces bursts of radiation that could affect the planet's atmosphere and surface conditions. Imagine a world tidally locked, with one side facing the star in constant light and the other in permanent darkness, while powerful stellar flares sweep across the sky. Despite these challenges, Proxima Centauri b remains one of the most promising targets for study because of its proximity. Future telescopes may be able to analyze its atmosphere, searching for gases that hint at habitability. Its closeness also makes it a candidate for exploration concepts like Breakthrough Starshot, which envisions tiny probes traveling to the system within a human lifetime. Proxima Centauri b symbolizes the possibility of nearby habitable worlds. The TRAPPIST-1 system, located about 40 light-years away, is one of the most remarkable exoplanet discoveries. It contains 7 Earth-sized planets orbiting a small, cool red dwarf star. 3 of these planets lie within the habitable zone, where liquid water could exist on their surfaces. The system was first revealed in 2016 and studied further with NASA's Spitzer Space Telescope. Each planet has an orbit lasting from a day to 2 weeks, making the system compact but stable. Imagine standing on one of these worlds and seeing the other planets as bright objects in the sky, appearing larger than our Moon does from Earth. The planets likely have rocky surfaces, and some may have atmospheres or even oceans. TRAPPIST-1 has become a prime target for the James Webb Space Telescope, which can study the planet's atmospheres in detail. Its discovery excited scientists because it showed that a single star could host multiple Earth-sized worlds, raising the chances of finding habitable conditions. The TRAPPIST-1 system highlights the diversity of planetary systems in the galaxy and offers a nearby laboratory for studying planets that resemble Earth in size and potential habitability. WASP-12b is a hot Jupiter about 1,400 light-years away, orbiting so close to its star that it is being torn apart by gravity. The planet completes an orbit in just over 1 Earth day, placing it only a few million kilometers from its star. At this distance, Tidal forces stretch the planet into an oval shape, while its atmosphere is slowly being stripped away. Observations show that material from WASP -12b is spilling into the star, creating a trail of gas. Imagine a giant world glowing with heat, distorted by its star's pull and losing mass every second. Temperatures on WASP -12b exceed 2000 degrees Celsius, hot enough to break apart molecules. The planet is expected to be destroyed within a few million years, a short lifespan compared to most planets. Its extreme conditions give astronomers a rare chance to study how intense gravity and heat affect a planet's structure and atmosphere. WASP -12b serves as a striking example of how close orbiting gas giants can face violent ends, showing the destructive power of their host stars. HD 209458b, located about 150 light-years away, was the first exoplanet observed to have an atmosphere. Discovered in 1999, it is a hot Jupiter that orbits its star in about 3.5 days. Its atmosphere was detected when starlight passed through it during a transit, revealing sodium in its outer layers. Later studies found that the planet's atmosphere is escaping into space, forming a large cloud of hydrogen. Imagine a giant planet orbiting so near its star that its upper atmosphere is boiling away, leaving a comet-like tail stretching into space. This made HD 209458b a landmark discovery, proving that astronomers could study the atmospheres of distant planets, not just detect their presence. Follow-up research also revealed water vapor, carbon monoxide, and methane, showing the potential for detailed atmospheric science. The planet's unique status as the first, with a confirmed atmosphere, earned it the nickname Osiris, after the Egyptian god associated with rebirth, reflecting how it reshaped planetary science. GJ1214b is a super-Earth located about 40 light-years away, often called a water world. Discovered in 2009, it is about 2.7 times Earth's diameter and orbits a red dwarf star every 38 hours. Its density suggests it is not purely rocky, but contains large amounts of water or other volatiles. Astronomers believe it could have a deep ocean beneath a thick atmosphere of water vapor or hydrogen. Imagine a planet covered entirely by sea, with no land in sight, its atmosphere dense and steamy. Temperatures are too high for Earth-like conditions, but the presence of so much water makes GJ1214b unique. In 2021, new observations confirmed that its atmosphere is rich in water vapor or other molecules, supporting the water world model. While unlikely to host life as we know it, GJ1214b is valuable for studying planets. Unlike any in our solar system, its discovery showed that water-rich worlds may be common in the galaxy, expanding ideas about planetary diversity. Kepler-16b is a circumbinary planet, orbiting 2 stars instead of 1. Discovered in 2011, it lies about 200 light-years away. The planet is similar in size to Saturn and has a cold, gaseous composition. Its 2 parent stars, a red dwarf and a Sunday-like star, orbit each other, while the planet circles both in a stable path. Imagine standing on Kepler-16b's surface, if it had one, and seeing 2 suns in the sky, rising and setting together, or at different times, creating shifting light and shadows. The discovery confirmed that planets can form and survive in binary star systems, once thought too unstable for planets. Kepler-16b's orbit is about 229 days long, similar to Venus's year, but its cold atmosphere means it is not habitable. Its existence proves that planetary systems are more varied than once expected, showing that worlds can thrive even in the complex gravitational dance of twin stars. WASP-76b is an ultra-hot Jupiter, located about 640 years away, known for its extreme conditions. The planet orbits its star in less than 2 days, exposing one side to constant heat, while the other remains cooler. Temperatures on the day side soar above 2,400 degrees Celsius. Observations suggest that iron vapor rises in the atmosphere on the day side and then condenses on the cooler night side, falling as iron rain. Imagine a sky where droplets of molten metal sweep across stormy winds, creating a landscape beyond anything on Earth. The planet is tidally locked, meaning the same side always faces its star, which drives violent winds moving heat and vapor between hemispheres. WASP-76b demonstrates the extremes possible for planetary atmospheres, where familiar elements like iron behave in alien ways. It stands as one of the most dramatic examples of how hostile exoplanets can be, turning everyday materials into part of a bizarre, deadly weather cycle. Spectroscopy is the main tool used to study exoplanet atmospheres. When a planet passes in front of its star, some starlight filters through the planet's atmosphere before reaching Earth. This light carries imprints of the gases present, which astronomers can detect by splitting it into spectra. Different molecules absorb specific wavelengths, leaving recognizable patterns. The same technique works when a planet moves behind its star, allowing scientists to compare starlight with and without the planet's contribution. This reveals information about temperature, composition, and sometimes even wind speeds. For example, the first atmospheric detection on HD 209458b came through sodium seen in its spectrum. Imagine holding up a prism to sunlight and noticing faint missing colors. Each missing shade tells you what elements are present. Spectroscopy not only identifies gases, but also hints at pressure and chemical processes. With powerful instruments like the James Webb Space Telescope, astronomers can now study atmospheres of smaller planets, looking for water vapor, carbon dioxide, and other molecules linked to habitability. This technique turns faint signals of distant worlds into detailed profiles of their skies, giving insight into what conditions might exist on planets far beyond our solar system. Water vapor has been detected in the atmospheres of several exoplanets, often giant planets orbiting close to their stars. When starlight passes through their atmospheres, spectral lines reveal water molecules absorbing specific wavelengths. For example, Hubble Space Telescope observations of WASP-12b and HAT-P-11b showed strong evidence of water vapor. The presence of water does not mean these worlds are habitable. Many are too hot, with steam-filled skies, but it proves that water is common in planetary atmospheres. Imagine a gas giant with layers of cloud, where instead of thin wisps like on Jupiter, the air is thick with vapor rising from deep layers. On smaller rocky exoplanets, water vapor would be even more significant, hinting at the possibility of oceans. Detecting it in the right conditions, such as in a temperate zone, could be a sign of habitability. With the James Webb Space Telescope, astronomers are now able to search for water vapor on Earth-sized planets. Finding it shows not only what their atmospheres are made of, but also expands the search for planets where liquid water and possibly life could exist. Methane has been detected in a handful of exoplanet atmospheres, providing clues about chemistry and potential habitability. On giant planets, methane forms naturally at high pressures and low temperatures, so its presence often fits models of gas-rich atmospheres. For example, methane was observed on exoplanets such as HD 189733b and GJ 436b. Detecting methane on smaller rocky planets could be more significant. On Earth, methane has both geological and biological sources, so finding it in the right context may point to interesting processes. Imagine scanning the spectrum of a planet and seeing the telltale lines of methane absorption, like a chemical fingerprint from its skies. However, methane is difficult to confirm because signals can overlap with those from water vapor or other gases. Instruments like the James Webb Space Telescope are improving accuracy, allowing astronomers to better separate these features. Methane by itself is not proof of life, but combined with gases like oxygen, it could be a stronger biosignature. Its detection adds to the growing evidence that exoplanet atmospheres are complex and diverse, with chemistry shaped by temperature, pressure, and the type of star each planet orbits. Sodium and potassium are among the most common elements detected in exoplanet atmospheres. Their strong absorption lines make them easier to spot with spectroscopy. They were first identified in the atmosphere of HD 209458b, where sodium created a clear signal during transit observations. These elements often appear in the upper layers of hot gas giants, where high temperatures keep them in vapor form. Imagine a planet glowing under its star's heat, with its skies tinted faintly by sodium and potassium gases. Their detection helps astronomers measure atmospheric structure, since the depth and shape of the absorption lines reveal pressure and temperature at different layers. On cooler planets, sodium and potassium may condense out, so their absence can also provide important clues. These elements are not linked directly to habitability, but they are key tracers for understanding planetary atmospheres. By studying their presence, astronomers refine models of how atmospheres expand, circulate, and interact with starlight. Sodium and potassium continue to serve as reliable markers, proving that even simple elements can tell complex stories about distant worlds. Exoplanets can have clouds made of exotic materials unlike anything on Earth. On very hot worlds, such as ultra-hot Jupiters, temperatures are high enough for silicates, iron, or even corundum, the mineral in sapphires and rubies, to condense and form clouds. Observations of WASP-121b suggest clouds of metal oxides, while WASP-76b may even have iron condensing into raindrops. Imagine skies filled with shimmering mineral dust, with storms that rain molten metal instead of water. These exotic clouds affect the spectra astronomers record, sometimes masking or distorting signals of gases like water vapor. They also play a role in a planet's climate, reflecting starlight and trapping heat. On smaller, cooler planets, clouds could still be familiar, made of water or methane, but the most extreme exoplanets push the boundaries of what is possible. Detecting exotic clouds challenges existing models of atmospheric physics, since they form under conditions far removed from Earth's. By studying them, astronomers learn how temperature, chemistry, and pressure shape planetary skies, showing that alien weather systems can be as varied and strange as the planets themselves. These findings highlight the diversity of atmospheres across the galaxy. Hot Jupiters often appear puffier than expected, with atmospheres that are swollen and extended. Their close proximity to their stars heats their outer layers, causing gases to expand and reducing the planet's overall density. For example, Washington SP-17b has a radius nearly twice that of Jupiter, despite having less mass, making it one of the puffiest known exoplanets. Imagine a balloon heated so much that it stretches far beyond its usual size, thin but wide. Stellar radiation and strong winds drive this inflation, while tidal interactions may add further energy. The puffiness allows astronomers to study their atmospheres more easily, because the expanded layers absorb more starlight during transits. This makes spectral signals stronger, helping identify gases like water vapor, sodium, and potassium. Although these worlds are unlikely to host life, their inflated atmospheres provide valuable laboratories for understanding heat-driven atmospheric physics. The study of puffiness also helps explain why some gas giants lose mass over time, with their bloated layers escaping into space. Hot Jupiters show how extreme radiation and gravity can reshape a planet, producing worlds that differ dramatically from the gas giants in our own solar system. Some exoplanets lose parts of their atmospheres so rapidly that the escaping gases form tails resembling comets. These features occur when a planet orbits close to its star and intense radiation strips away hydrogen, helium, or heavier elements. For example, HD 209458b shows a vast cloud of hydrogen trailing behind it, revealed through ultraviolet observations. Imagine a gas giant racing around its star, shedding material that streams out into space like smoke from a fire. These tails can stretch for millions of kilometers, showing just how powerful stellar radiation can be. Smaller, rocky planets close to their stars may also lose atmospheres this way, leaving behind barren worlds. The study of escaping atmospheres helps explain planetary evolution, showing why some planets shrink over time or transform from gaseous bodies into rocky remnants. Tails also provide direct evidence of atmospheric composition, since the escaping material leaves clear spectral fingerprints. Observing these structures gives astronomers a window into processes that shape planetary systems, revealing how stars can strip, sculpt, or even destroy the atmospheres of their planets. The James Webb Space Telescope, JWST, is transforming the study of exoplanet atmospheres. With its powerful infrared instruments, JWST can detect faint signals from small, rocky planets that earlier telescopes could not analyze in detail. By observing transits and eclipses, it records spectra that reveal gases such as water vapor, carbon dioxide, and methane. For example, JWST has already studied the TRAPPIST-1 system, searching for atmospheric features around its Earth-sized planets. Imagine a telescope sensitive enough to catch the fingerprints of molecules in a thin layer of air on a planet, dozens of light years away. JWST's precision also allows astronomers to measure temperature gradients, cloud layers, and chemical interactions in planetary skies. Its ability to study smaller and cooler planets expands the search for habitability, moving beyond hot Jupiters and gas giants. By combining data from JWST with ground-based observatories, scientists are beginning to build detailed atmospheric profiles. The telescope marks a new era in exoplanet science, making it possible to explore conditions on worlds that resemble Earth, as well as those that are utterly alien. Atmospheric data can provide hints about whether a planet might be habitable. The presence of gases like water vapor, carbon dioxide, and nitrogen can suggest stable climates where liquid water may exist. Ratios of greenhouse gases reveal whether a planet is too hot, too cold, or within a balanced range. For example, a rocky planet in a star's habitable zone with detectable water vapor would be a strong candidate for further study. Imagine analyzing a spectrum and finding the unmistakable signs of water alongside carbon dioxide in the right amounts to regulate temperature. This combination could indicate Earth-like conditions. Clouds and haze can complicate readings, but also provide clues about weather systems and atmospheric depth. Even if habitability cannot be confirmed, atmospheric profiles narrow the search to planets most likely to support life. While many exoplanets studied so far are too hot or too gaseous, the growing ability to analyze smaller planets means the first truly Earth-like world may be identified in the coming years. Atmospheres remain one of the most direct windows into whether distant worlds could sustain life. Biosignatures are chemical clues in a planet's atmosphere that may indicate life. On Earth, oxygen and methane coexist because living organisms replenish them. Without life, they would react away quickly. Detecting such imbalances on another planet could signal biological processes. For example, a spectrum showing both methane and oxygen in a rocky planet's atmosphere would be highly intriguing. Imagine scanning starlight from a distant world and finding patterns that match Earth's life driven chemistry. Other possible biosignatures include nitrous oxide, chloromethane, or unusual ratios of gases that cannot be explained by geology alone. However, scientists must rule out non-biological sources, since volcanic or chemical processes can mimic these signals. The search for biosignatures focuses on planets in habitable zones where liquid water could exist. The James Webb Space Telescope and future missions aim to measure these gases in Earth-sized planets around nearby stars. Finding a true biosignature would not prove life instantly, but would mark the strongest evidence yet. It represents the ultimate goal of atmospheric studies, learning whether Earth is unique or one of many living worlds in the galaxy. The habitable zone is the region around a star where conditions allow liquid water to exist on a planet's surface. It depends on the star's temperature and brightness. Around a star like the Sunday, the habitable zone lies roughly between the orbits of Venus and Mars. Planets inside this zone are not guaranteed to be habitable, but they have the right balance of heat for water to stay liquid rather than boiling away or freezing solid. For example, Earth is well placed in the Sunday's habitable zone, while Venus is too hot and Mars is too cold. Imagine drawing a band around a star where the light is not too strong and not too weak, like the warm space near a campfire. Astronomers focus on this region when searching for planets, because water is essential for life as we know it. The discovery of exoplanets, such as Kepler -22b and Kepler -186f, in their stars' habitable zones, shows that Earth-like conditions may be common. The habitable zone remains a starting point for judging habitability, even though atmosphere, geology, and other factors are also critical in shaping a planet's true environment. Planets too close to their stars face runaway greenhouse effects, where heat builds uncontrollably. This happens when intense starlight causes water to evaporate into the atmosphere. Water vapor, a powerful greenhouse gas, traps even more heat, driving temperatures higher until oceans boil away. Venus is the best example in our solar system, with a thick atmosphere of carbon dioxide and surface temperatures hot enough to melt lead. Imagine standing on such a planet where the sky is dense, clouds glow with acid droplets, and the ground blazes under crushing heat. In exoplanet systems, many planets detected close to their stars are thought to share these conditions. Even if they orbit in what seems to be the habitable zone, strong greenhouse effects can push them beyond habitability. Studying these worlds helps astronomers understand how climate spirals into extremes and why some planets lose water permanently. The runaway greenhouse effect is a warning that habitability depends on more than distance. The atmosphere plays a decisive role in shaping a planet's surface conditions. Planets orbiting too far from their stars fall into freezing conditions. With insufficient heat, water turns to ice, and atmospheres can collapse as gases freeze onto the surface. Mars offers a local example. Although it lies near the Sunday's habitable zone, its thin atmosphere cannot hold enough heat, leaving it cold and dry. For exoplanets, this means many worlds found beyond the habitable zone are frozen. Even if they are Earth-sized, imagine standing on such a planet under a weak, distant sun, where glaciers stretch across the landscape and oceans lie buried beneath thick ice sheets. While surface life is unlikely, subsurface oceans could still exist, warmed by internal heat. For instance, icy moons in our solar system, like Europa and Enceladus, show that life might survive below frozen exteriors. Similarly, frozen exoplanets may hold hidden water beneath their shells. The possibility of these underground habitats keeps them scientifically interesting, even though they lie beyond the classic habitable zone. Freezing conditions remind us that not all life-friendly environments need sunlight, expanding the range of places where habitability can be considered. Red dwarf stars are the most common in the galaxy, and their habitable zones are very close. Because these stars are small and cool, planets must orbit tightly to receive enough warmth for liquid water. This means their habitable zones are much narrower than the Sunday's. For example, Proxima Centauri b lies in the habitable zone of its red dwarf star, with an orbit of only 11 days. Imagine a planet where the star looms large in the sky, glowing red and faint compared to our Sunday, yet providing the right amount of heat because of the close orbit. Many red dwarf planets are tidally locked, with one side in constant daylight and the other in endless night. This creates unique climates where habitability may depend on atmospheric circulation or heat transfer. Since red dwarfs are so common, their habitable zones offer many chances to find Earth-sized worlds. However, their closeness also brings risks, as planets are more exposed to stellar activity and gravitational locking. Still, these stars remain central targets in the search for potentially habitable exoplanets. Red dwarf stars often produce powerful stellar flares that may threaten habitability. These bursts release intense radiation and charged particles, which can strip away planetary atmospheres or damage surface conditions. For a planet orbiting close to a red dwarf, as it must to stay in the habitable zone, the impact of flares can be severe. Imagine living on a world where the sky suddenly lights with violent bursts, and the thin atmosphere struggles to shield the surface from radiation. Proxima Centauri, the nearest red dwarf, is known for such flares, raising questions about whether Proxima Centauri b could retain an atmosphere. Some models suggest that a strong magnetic field or dense atmosphere might protect these planets, redistributing heat and shielding life. Others warn that repeated flares over billions of years may sterilize the surface. Studying these effects helps astronomers weigh the balance between opportunity and risk in red dwarf systems. Stellar flares highlight how habitability is shaped, not only by location in the habitable zone, but also by the star's activity and the planet's ability to withstand harsh space weather. Magnetic fields could protect exoplanets from harmful radiation and stellar winds. On Earth, the magnetic field deflects charged particles from the Sunday, creating auroras near the poles, but shielding the atmosphere from being stripped away. Without it, Earth's air and oceans might have been lost long ago. For exoplanets, especially those orbiting close to active stars, a magnetic field could mean the difference between retaining an atmosphere or becoming barren. Imagine a rocky planet around a red dwarf, bombarded by flares, but with magnetic lines curving outward like invisible armor, turning most of the charged particles aside. Detecting magnetic fields directly is difficult, but scientists look for hints, such as radio emissions caused by interactions with stellar winds. Gas giants, like Jupiter, are thought to produce strong fields, while smaller rocky worlds may vary depending on their cores and rotation. The presence of a magnetic field adds another factor in assessing habitability. Even if a planet lies in the habitable zone, without magnetic shielding its surface may be too exposed to support life. This makes the study of planetary magnetism crucial in the broader search for habitable worlds beyond Earth. Tidal locking occurs when a planet always shows the same side to its star, creating extreme climates. The star-facing side bakes under constant light, while the far side remains in permanent darkness. Temperatures can soar on one hemisphere and plunge on the other. Many exoplanets around red dwarfs are likely tidally locked because their orbits are close. Imagine standing on the day side, where the sun never moves in the sky, casting eternal noon, while on the other side, endless night freezes the land. The border between light and dark, known as the terminator, could have moderate conditions where water might stay liquid. Models suggest that a thick atmosphere or deep oceans could redistribute heat, softening the contrast between hemispheres. Strong winds may also transport warmth, creating more stable climates. While tidal locking was once thought to rule out habitability, new studies show that some locked planets could still support life, especially in regions where temperature extremes balance. These unusual conditions highlight the diversity of environments where life might adapt, even under skies very different from Earth's. Oceans play a key role in regulating temperatures on Earth, and they may serve the same function on exoplanets. Water absorbs heat slowly and releases it gradually, preventing wild temperature swings between day and night. This stabilizing effect could be even more important on tidally locked planets, where oceans might carry warmth from the star. Facing side to the colder dark side, imagine a planet covered in global seas, with currents flowing endlessly between hot and frozen regions, creating a balanced climate that allows habitability. On Earth, oceans also drive weather systems and store carbon, helping maintain a stable atmosphere over long timescales. Exoplanets with large amounts of surface water, often called water worlds, may benefit from similar processes. Even if their skies are cloudy or their stars variable, oceans could act as buffers against change. Detecting liquid water directly is difficult, but signs such as water vapor in the atmosphere or a planet's density suggesting a water-rich composition hint at their presence. Oceans may be one of the strongest indicators that a planet can remain habitable for billions of years. Atmospheres are essential for making planets habitable. They trap heat, protect surfaces from harmful radiation, and allow stable climates where liquid water can exist. On Earth, the atmosphere contains nitrogen, oxygen, and trace gases that regulate temperature and support life. Without it, Earth would be a frozen, airless rock. For exoplanets, an atmosphere can be the deciding factor in whether they are truly habitable, even if they orbit in the habitable zone. Imagine two planets at the same distance from a star. The first may support life, while the second remains sterile. Thick atmospheres can also create problems, as seen on Venus, where a runaway greenhouse effect turned the planet into a furnace. Astronomers study exoplanet atmospheres using spectroscopy, looking for gases such as water vapor, carbon dioxide, and methane. These gases reveal not only the climate, but also possible biological activity. Atmospheres are fragile, easily lost to strong stellar winds unless protected by magnetic fields. Their presence is one of the most important signs that a world could support life. Earth remains the only known habitable planet, home to complex life sustained by liquid water, a stable atmosphere, and a protective magnetic field. Its location in the Sunday's habitable zone provides the right balance of warmth, while oceans and weather systems regulate climate. Earth's biosphere thrives in diverse environments, from deep oceans to mountain peaks, showing how adaptable life can be. Imagine an astronomer on a distant world studying Earth's light. They would see water vapor, oxygen, and methane in its spectrum. Clear signs of habitability. Despite thousands of exoplanets discovered, none yet show conclusive evidence of life. Some, like Kepler-186f or Proxima Centauri b, lie in habitable zones, but details about their atmospheres and surfaces remain uncertain. Earth serves as both an example and a benchmark. By comparing other planets to it, scientists judge whether conditions might be suitable for life. The search continues. But so far Earth stands alone, a rare blue world filled with oceans, clouds, and green landscapes, orbiting a star that has remained stable for billions of years. It is our best model for understanding habitability in the universe. Many stars host multiple planets, forming systems as diverse as or more diverse than our own. Observations from Kepler and TESS show that multi-planet systems are common in the Milky Way. Some resemble miniature versions of the solar system, with planets spread out in ordered orbits, while others place several worlds much closer to their stars. For example, Kepler-90 is known to host at least 8 planets, matching the solar system in number, but with very different arrangements. Imagine looking at such a system from above, planets tracing paths that weave tightly around their star, each influencing the orbits of its neighbors. Multi-planet systems provide opportunities to study how worlds interact through gravity, sometimes causing orbital resonances where planets move in synchronized rhythms. These resonances can stabilize or destabilize entire systems over time. By comparing many examples, astronomers learn how planets form, migrate, and settle into long-term orbits. The discovery that multi-planet systems are common challenges the idea that the solar system is unique, instead showing that stars across the galaxy often have families of planets circling them. The TRAPPIST-1 system, about 40 light-years away, is remarkable for hosting 7 Earth-sized planets around a cool red dwarf star. Discovered between 2016 and 2017, the system quickly became a focus of exoplanet research. 3 of the planets lie in the star's habitable zone, where liquid water could exist on their surfaces. All 7 orbit very close to their star, with years lasting from 1.5 to 19 days. Yet the system is stable thanks to a chain of orbital resonances. Imagine standing on one of these worlds and seeing several neighboring planets looming large in the sky, brighter than the Moon appears from Earth. TRAPPIST-1 star is small and faint, so despite the close distances, the planets receive similar energy levels to those in our own habitable zone. Their sizes and densities suggest rocky compositions, making them prime candidates for atmospheric studies with the James Webb Space Telescope. The TRAPPIST-1 system demonstrates how even tiny stars can host complex planetary families, some with the potential for habitability, and it offers one of the best opportunities to search for life beyond the solar system. Some exoplanetary systems are compact, with planets orbiting closer to their stars than Mercury does to the Sun. These planets often crowd into small regions with multiple orbits fitting inside what would be Earth's orbit in our solar system. For example, the Kepler-11 system has 6 planets packed within a zone smaller than Venus's orbit. Imagine looking up at the sky from such a world and seeing neighboring planets appear bright and close, crossing in and out of view regularly. Compact systems challenge earlier theories that expected planets to spread out more widely. They show how planetary migration during formation can bring worlds inward, creating tight arrangements. Many compact systems include super-Earths and mini-Neptunes, types of planets that do not exist in our solar system. Their orbits can remain stable thanks to resonances, where planets tug on each other in repeating patterns. Compact systems highlight the variety of planetary architectures, proving that not all stars follow the wide spacing seen in our solar system. Instead, some stars host crowded neighborhoods of planets, orbiting in rapid succession. Other planetary systems feature planets with wide orbits that take decades or even centuries to complete. Gas giants in these systems can resemble or exceed Jupiter, circling far from their stars at distances of tens or hundreds of astronomical units. Because of their long orbital periods, detecting such planets requires years of monitoring. Direct imaging is often the best method, as these wide-orbit planets are far enough from their stars to be seen separately. For example, the HR 8799 system includes 4 massive planets in wide orbits, each captured through direct imaging. Imagine a planet circling so far out that its year lasts longer than human lifetimes. Moving slowly across the sky from wide-orbit planets are important for understanding planetary formation, as they may have formed in situ or migrated outward through interactions with other planets. Their presence also influences the structure of debris, disks, and smaller objects, shaping entire planetary systems. These distant worlds demonstrate that not all planets huddle close to their stars. Some drift far away, bound by gravity yet isolated in cold, distant orbits. Exoplanet orbits can be highly eccentric, creating extreme climates. Unlike Earth's nearly circular orbit, an eccentric orbit takes a planet much closer to its star at one point and much farther away at another. Temperatures swing dramatically during each orbit, with scorching conditions near the star and freezing cold at the farthest point. For example, HD 80606b has one of the most eccentric orbits known, plunging close to its star before swinging back out. With a year lasting about 111 days, imagine living on such a planet where seasons are not gradual but violent, with sudden bursts of heat followed by long freezes. Eccentric orbits can result from gravitational interactions with other planets or passing stars. They raise questions about habitability, since stable climates are difficult under such extremes. However, they also reveal the chaotic nature of planetary systems and how gravitational forces shape their evolution. Studying eccentric exoplanets helps astronomers understand how orbits settle or fail to settle over time. These worlds highlight the diversity of planetary motions, showing that not all planets follow smooth, circular paths like Earth. Resonances occur when planets influence each other's orbits through gravity, locking into repeating patterns. In these cases, orbital periods form simple ratios, such as 2:1 or 3:2. For example, if one planet completes 2 orbits in the same time another completes 1, their motions reinforce each other. This stabilizes the system and can prevent collisions. The TRAPPIST-1 planets are a well-known example, with all 7 locked in a resonance chain that keeps their compact system orderly. Imagine planets moving like dancers in a rhythm, each step timed to avoid stepping on the other's path. Resonances can also create detectable variations in transit timing, allowing astronomers to confirm planets that might otherwise be missed. While resonances can stabilize, they may also amplify disturbances if disrupted, leading to chaos. Studying them reveals how planets settle into long-term configurations. Resonances are not rare, but widespread across exoplanetary systems, showing that gravity sculpts orbits in predictable, yet sometimes fragile ways. Some planetary systems remain stable for billions of years, even when filled with multiple planets in close orbits. Stability depends on the balance of gravity between planets and their star. If orbits are well spaced or locked in resonances, planets can circle peacefully for immense timescales. For example, simulations suggest that the TRAPPIST-1 system could remain stable for billions of years, despite its crowded layout. Imagine a clockwork machine with gears turning endlessly, each part moving smoothly without collision. Such stability allows conditions for life to develop, since planets need steady climates over long periods. In contrast, unstable systems may eject planets or cause collisions, reshaping their architecture. The fact that astronomers observe many stable systems today shows that long-lived configurations are common. These findings help refine models of planet formation and evolution, proving that order can emerge from the chaotic early stages of planetary birth. Stability remains one of the key factors in deciding whether planets can support life over geological timescales. Many planetary systems show evidence of past migration, where planets shifted from their original birthplaces. Migration occurs when planets interact with the gas and dust of their protoplanetary disks or with other planets. Gas giants often move inward, sometimes pulling smaller planets with them, or disrupting their orbits. Evidence for migration comes from compact systems with large planets close to their stars, positions unlikely for their initial formation. For example, hot Jupiters like 51 Pegasi b must have formed farther out before spiraling inward. Imagine a planetary system in its early days, with orbits shifting as massive planets plow through the disk like ships through water. These movements can scatter smaller bodies, explaining why some systems lack inner rocky planets. Migration also helps explain resonances, as planets can be captured into synchronized orbits while moving inward or outward. Tracing these signs in today's systems gives astronomers a glimpse of their violent pasts, showing that planetary orbits are not always fixed from the beginning, but evolve over time. Gas giants often migrate inward from where they formed. These planets are believed to originate beyond the snowline, where icy material is abundant enough to build massive cores. Interactions with the protoplanetary disk then cause them to spiral closer to their stars. This explains the existence of hot Jupiters, gas giants orbiting within just a few days. For example, Washington SP-12b orbits so near its star that it is being stripped apart, a fate linked to its migration. Imagine a Jupiter-sized world dragged inward until it circles closer than Mercury does to the Sunday. Its thick atmosphere blasted by radiation, such inward movement reshapes planetary systems, sometimes destroying or ejecting smaller planets. In the process, inward migration was a surprise discovery, because early models expected gas giants to remain far out like Jupiter and Saturn. Now it is recognized as a common process, helping explain the diversity of planetary architectures. Studying migrating giants reveals the dynamic forces that sculpt systems, showing how planets and disks interact in their formative years. Migration shapes the overall architecture of planetary systems, determining where planets end up and how they interact. Without migration, most planets would remain near their birthplaces. But observations show a wide variety of arrangements. Some systems are tightly packed with multiple super-Earths, while others feature hot Jupiters dominating inner orbits. Migration explains these differences, as planets move through their disks, capture others into resonances, or scatter smaller bodies. Imagine building a model solar system, only to see the pieces slide around as invisible hands rearrange them. The end result depends on the timing and strength of migration. Systems with gentle migration may settle into stable chains, while violent migration can leave planets on eccentric orbits or remove them altogether. By studying system architectures today, astronomers infer how migration shaped their histories. This process highlights that planetary systems are not static creations, but evolving structures shaped by movement. Migration is one of the key reasons exoplanetary systems show such a wide range of designs compared to our own solar system. Exoplanet science gives direct insight into how planets form. Early theories were based only on the solar system, which seemed orderly, with rocky planets close in and gas giants far out. The discovery of hot Jupiters and tightly packed systems overturned this picture, proving that planets can migrate and settle in unexpected places. Observations show that disks of gas and dust around young stars create planets of many sizes and types. Imagine a star in its infancy surrounded by a swirling disk where small grains stick together, growing into worlds. By comparing thousands of exoplanets, astronomers see patterns, such as the common occurrence of super-Earths and mini-Neptunes, which our system lacks. These comparisons refine models of accretion, migration, and stability. Exoplanets also reveal the effects of stellar mass and chemistry on planet formation. For instance, stars richer in heavy elements tend to host more gas giants. The study of exoplanets turns theories into tested science, showing that planet formation is not a single recipe, but a variety of processes. This broad view explains both our solar system's structure and the remarkable diversity of systems across the galaxy. Studying exoplanets allows scientists to test theories of planetary atmospheres under conditions very different from Earth. Hot Jupiters show how radiation inflates and strips gaseous layers, while super-Earths and mini-Neptunes reveal the role of pressure and composition in shaping climates. Imagine watching the spectrum of a distant star dip slightly as a planet transits, carrying with it the faint fingerprints of gases. Each observation confirms or challenges models built from physics and chemistry. For example, sodium and potassium detected in hot gas giants support predictions of atmospheric structure, while unexpected clouds of exotic materials like silicates force new adjustments. The James Webb Space Telescope adds detail, detecting water vapor and carbon dioxide on smaller planets. Comparing atmospheres across many types of worlds helps scientists understand what factors drive climate, stability, and potential habitability. These studies also link back to Earth, showing how greenhouse effects, cloud layers, and chemical cycles operate on different scales. By testing and refining theories, exoplanet science strengthens our grasp of atmospheres, both here and across the galaxy. Exoplanets may hold vital clues about the origins of life. Life on Earth depends on liquid water, stable climates, and chemical building blocks. By studying planets with similar conditions, scientists can ask whether life is likely to emerge elsewhere. Imagine discovering a rocky world with oceans and an atmosphere rich in carbon dioxide, nitrogen, and traces of methane. Such conditions could resemble Earth billions of years ago, when life first appeared. Some exoplanets in habitable zones show hints of water vapor, while others reveal chemistry that could support prebiotic reactions. Even if no life is found, these planets show how common or rare Earth-like conditions might be. By comparing different systems, scientists learn whether life arises easily when the right ingredients exist, or whether Earth is unusual. Exoplanets also expand the range of environments considered for life, such as subsurface oceans on water worlds or moons around giant planets. The search for life beyond Earth is one of the deepest motivations for exoplanet research, linking astronomy with biology and chemistry. Each discovery brings us closer to understanding whether we are alone. Exoplanets reveal the incredible diversity of planetary systems. Some stars host compact families of planets packed inside Mercury's orbit, while others spread gas giants across wide orbits lasting centuries. There are rocky super-Earths, puffy hot Jupiters, icy giants, and water worlds unlike anything in our solar system. Imagine comparing our orderly system with another, where a Jupiter-sized planet skims close to its star, while smaller worlds orbit farther out. This variety challenges the idea that our system is typical. It also shows how migration, stellar type, and initial disk composition shape final outcomes. The TRAPPIST-1 system demonstrates how even a faint red dwarf can host 7 Earth-sized planets, while HR 8799 shows a wide system of massive gas giants. By cataloguing these differences, astronomers build a clearer picture of how planets form and evolve under different conditions. The diversity of exoplanets proves that planetary systems come in many designs, often stranger than expected, and highlights the need to study many examples rather than relying only on our own. Some exoplanets may harbor moons, and these moons could be habitable even if their parent planets are not gas giants. Inhabitable zones could host large rocky moons with liquid water and atmospheres. Imagine a moon orbiting a giant planet where the sky is dominated by the massive world above while sunlight warms oceans below. Tidal forces from the planet could provide additional heat, keeping subsurface oceans liquid even if surface conditions vary. In our solar system, moons like Europa, Enceladus, and Titan show that habitability is not limited to planets. Detecting exomoons is difficult, but researchers search for small variations in transit timing or dips in starlight caused by moons crossing stars. So far, no exomoon has been confirmed, but candidates such as Kepler-1625b, I suggest they may exist. If proven, exomoons would expand the potential for life across the galaxy, since giant planets are common and may carry multiple moons. They represent one of the most exciting frontiers in exoplanet science, showing that habitable environments may exist in unexpected places, circling not stars but other worlds. Exomoons are harder to detect than exoplanets, but they remain possible targets for observation. Unlike planets, which block noticeable amounts of starlight during transits, moons create only subtle signals. Astronomers look for variations in a planet's transit timing or slight dips in brightness that suggest a moon is also passing in front of the star. Imagine watching a planet's shadow cross a star and noticing tiny shifts as though a smaller companion were tugging it along. So far, no exomoon has been confirmed, though candidates like Kepler-1625b I have raised interest. Detecting them requires extremely precise measurements, often pushing current instruments to their limits. Future telescopes with higher sensitivity may reveal these hidden companions. Exomoons matter because they could expand the number of potentially habitable worlds. Large moons orbiting giant planets in habitable zones might have liquid water and stable climates. In our solar system, moons like Europa and Titan show that these environments can exist, suggesting exomoons may be just as important as exoplanets in the search for life. Their discovery would open a new chapter in planetary science, showing that habitable conditions can exist around both stars and planets. Future telescopes may allow astronomers to capture direct images of Earth. Like planets, current imaging works best for massive planets, far from their stars. But Earth-sized worlds near habitable zones remain hidden by the glare of starlight. Advanced instruments will increase sensitivity, making it possible to isolate the faint light of small rocky planets. Imagine a telescope sharp enough to capture a pale blue dot orbiting another star. Much like Earth appears from space, such an image would provide more than just a picture. It would carry the planet's light, ready for analysis. Spectroscopy could reveal water vapor, carbon dioxide, or oxygen, giving strong clues about habitability. Missions like the planned Nancy Grace Roman Space Telescope are designed to take steps toward this goal, while future observatories may complete it. Direct imaging of Earth, like exoplanets, would mark a major milestone, offering the clearest look yet at worlds similar to our own. It would allow astronomers to compare Earth to distant planets in detail, strengthening the search for life. Space-based coronagraphs are designed to block out starlight, making it easier to image faint exoplanets nearby. A coronagraph works like placing a shield inside a telescope, dimming the bright star while letting the weaker glow of a planet come through. This technique is already used to study the outer atmospheres of stars, but new designs aim at capturing planets directly. Imagine trying to spot a firefly next to a lighthouse. A coronagraph acts like a mask that hides the lighthouse beam, leaving the firefly visible. Future missions, such as the Nancy Grace Roman Space Telescope, will include advanced coronagraphs capable of detecting smaller and dimmer planets than before. These instruments will help bridge the gap between indirect detection methods and true direct imaging. Coronagraphs are vital because they allow astronomers to study planetary atmospheres without interference, providing clean spectra that reveal key gases. By reducing the overwhelming brightness of stars, coronagraphs open the way to finding and analyzing planets that may otherwise remain hidden. Starshades are another promising technology for imaging exoplanets. Unlike coronagraphs placed inside telescopes, starshades are large structures flown separately in space. They position themselves thousands of kilometers away from a telescope, blocking starlight before it even reaches the instrument. Imagine an enormous flower-shaped screen unfurling in space, perfectly aligned to shield a telescope from a star's glare, while the faint light of orbiting planets slips past its edges. This approach could reveal Earth like planets near habitable zones by providing sharper contrast than coronagraphs alone. Designing starshades requires precision, as alignment must be exact. But the payoff could be transformative. Proposed missions combine space telescopes with starshades to achieve direct imaging of small rocky planets, potentially allowing detailed atmospheric studies. Starshades represent a bold step forward, creating conditions in space that ground-based telescopes cannot match. If realized, they could give humanity its first clear views of true Earth analogues around distant stars, making them one of the most exciting concepts for future exoplanet exploration. Discovering life elsewhere would be a monumental breakthrough, reshaping science and human perspective. Even the detection of microbial life on an exoplanet or moon would show that biology is not unique to Earth. Imagine confirming atmospheric biosignatures such as oxygen and methane existing together in balance, a chemical fingerprint of living processes. Such a discovery would prove that life can emerge under different conditions and that the universe may be filled with living worlds. The implications extend beyond science, influencing philosophy, religion, and our place in the cosmos. For astronomy, it would provide a framework for understanding how life begins and evolves. For society, it would mark a turning point in human history. Even if intelligent life remains undiscovered, proving that life exists elsewhere would answer one of humanity's oldest questions. Are we alone? The search continues with telescopes like JWST and planned missions designed to identify biosignatures. Each step brings us closer to the possibility of detecting life beyond Earth, a discovery that would echo across generations. Exoplanets are extremely faint when compared to their stars, making detection challenging. Stars shine with their own energy, while planets only reflect or emit a small fraction of that light. For a distant observer, the difference is immense. Imagine standing beside a stadium floodlight and trying to spot a glowing ember at its edge. The ember represents the planet. This faintness forces astronomers to rely on indirect methods such as the transit or radial velocity techniques. Even direct imaging requires instruments that can isolate a planet's tiny signal from overwhelming starlight. Infrared telescopes sometimes help, since planets can emit heat more strongly in those wavelengths. But the signal is still weak. The difficulty of capturing such faint light explains why most confirmed exoplanets are large, bright, and close to their stars. Smaller planets, like Earth, produce signals that are far harder to detect. Despite this, advances in optics and data analysis continue to improve sensitivity. Each detection adds to the growing catalogue of exoplanets, proving that even the faintest signals can be identified with patience and precision. This faintness challenge remains central to exoplanet science, shaping the methods and technology used in exploration. Stars outshine their planets by factors of billions, which makes direct observation nearly impossible without special techniques. The brightness difference is so extreme that a planet's reflected light is often drowned out completely. For example, an Earth-like planet orbiting a Sunday-like star would be 10 billion times fainter than its host star in visible light. Imagine trying to spot a candle flickering beside a searchlight. It is not that the candle lacks brightness, but that the searchlight overwhelms it. To deal with this, astronomers use tools such as coronagraphs and star shades, which block or reduce starlight. Spectroscopy during transits also sidesteps the issue by analyzing starlight filtered through a planet's atmosphere. Despite these methods, the brightness gap means that only a small number of planets have been directly imaged. Most discoveries rely on indirect techniques that measure changes in the star rather than light from the planet itself. This outshining effect explains why discovering planets is a technological feat, requiring sensitive instruments and innovative approaches to extract weak planetary signals from the glare of their stars. The vast distances to exoplanets make detailed study difficult. Even the closest star system, Proxima Centauri, is over 4 light-years away. Many discovered exoplanets are hundreds or thousands of light-years distant. which prevents sending probes or spacecraft to observe them directly. Instead, astronomers must rely on remote sensing, gathering faint light across immense distances. Imagine looking at a tiny speck of light across a desert and trying to deduce its landscape, weather, and chemistry from that single point. Distance also reduces the resolution of images, meaning planets cannot be seen as disks, but only as light curves or spectra. This limitation shapes the kind of data astronomers can collect. Broad features like mass, orbit, and atmospheric composition, but not surface details. Telescopes like the James Webb Space Telescope improve the situation by collecting more light and resolving finer signals. Yet distance remains a barrier. The dream of close-up study of exoplanets depends on future technology, such as interstellar probes, which remain theoretical. For now, distance forces scientists to interpret exoplanet properties from afar, piecing together worlds from the faintest of clues. False positives can mimic planetary signals, complicating exoplanet discovery. Stellar companions, background stars, or even instrument noise can create dips in brightness or wobbles in motion that look like planets. For example, binary star systems may produce transit, like signals, fooling early surveys. Imagine mistaking the shadow of a bird flying past a lamp for a planet passing in front of a star. The event seems similar, but comes from something else entirely. To reduce errors, astronomers use multiple methods to confirm planets. A transit signal might be checked with radial velocity data, or long-term observations may rule out stellar activity. The Kepler mission produced thousands of planet candidates, but only after years of follow-up did many gain confirmation. False positives are not failures, but part of the scientific process, reminding researchers to be cautious when interpreting faint signals. By refining techniques and demanding strong evidence, astronomers ensure that confirmed exoplanets are real. The challenge of false positives shows how delicate the search is and how much care goes into separating true planetary detections from misleading data. Small planets are the hardest to detect because their signals are faint and easily hidden by noise. A planet like Earth produces only a tiny dip in brightness during transit and an almost unmeasurable wobble in its star's motion. Larger planets, such as hot Jupiters, are far easier to find because their influence on their stars is much stronger. Imagine trying to spot the ripple of a pebble dropped in a large pond compared to the splash of a boulder. Current instruments favor the detection of big planets, which explains why many early discoveries were gas giants. Finding smaller, rocky planets requires extremely sensitive equipment and long observation times. Missions like Kepler and TESS have improved detection rates, showing that Earth-sized planets are common. Still, confirming them takes years of careful study. The James Webb Space Telescope may reveal more about their atmospheres, but their discovery remains at the edge of technological capability. Despite the difficulty, the search for small planets continues because they are the most likely to resemble Earth and to host life. Planets with long orbital periods take years to confirm, since astronomers must watch multiple cycles to prove a consistent signal. For example, Jupiter orbits the Sun every 12 years. Detecting a Jupiter-like planet elsewhere requires at least that long to gather clear evidence. Imagine trying to confirm the pattern of a pendulum that swings only once every few years. It demands patience and precision. Missions like Kepler often lasted less than a decade, making it difficult to confirm planets with orbits longer than a few years. As a result, most known exoplanets have short orbital periods, biasing discoveries toward close-in worlds. Long-period planets are important because they resemble those in our solar system, particularly gas giants and icy planets. They also influence the architecture of systems, affecting the stability of smaller inner planets. Detecting them requires persistence, long-term monitoring, and sometimes the use of multiple methods. While challenging, the gradual accumulation of data from observatories over decades is beginning to reveal more long-period planets, slowly filling in the picture of distant planetary systems. Systems with multiple planets create complex signals that can confuse detection. Each planet produces its own transits and wobbles, which can overlap and mimic other effects. For example, transit timing variations occur when one planet's gravity pulls on another, shifting the timing of their orbits. Imagine listening to several instruments playing different rhythms at once. Separating each melody takes careful analysis. In some cases, astronomers initially misinterpret signals as one planet when multiple are involved. Kepler data revealed that many stars host multi-planet systems, forcing the development of new models to untangle their signals. These interactions, while challenging, also provide opportunities. By studying variations, scientists can measure planet masses and even detect non-transiting planets indirectly. Multiple planet systems give insight into how worlds interact, migrate, and settle into stable arrangements. Despite the difficulties, they show the richness of planetary systems and provide some of the best opportunities to study dynamics. The complexity of their signals reflects the complexity of the systems themselves, offering both obstacles and rewards in exoplanet science. Systems with multiple planets create complex signals that can confuse detection. Each planet produces its own transits and wobbles, which can overlap and mimic other effects. For example, transit timing variations occur when one planet's gravity pulls on another, shifting the timing of their orbits. Imagine listening to several instruments playing different rhythms at once. Separating each melody takes careful analysis. In some cases, astronomers initially misinterpret signals as one planet when multiple are involved. Kepler data revealed that many stars host multi-planet systems, forcing the development of new models to untangle their signals. These interactions, while challenging, also provide opportunities. By studying variations, scientists can measure planet masses and even detect non-transiting planets indirectly. Multiple planet systems give insight into how worlds interact, migrate, and settle into stable arrangements. Despite the difficulties, they show the richness of planetary systems and provide some of the best opportunities to study dynamics. The complexity of their signals reflects the complexity of the systems themselves, offering both obstacles and rewards in exoplanet science. Direct imaging of exoplanets requires advanced optics to overcome the glare of stars. Techniques like coronagraphs block starlight inside telescopes, while adaptive optics correct for distortions caused by Earth's atmosphere. Together, these technologies allow astronomers to capture faint planetary light. Imagine wearing special glasses that block car headlights at night, letting you see the faint stars above more clearly. Advanced optics work in a similar way. Direct imaging is most effective for young, massive planets that emit their own heat and orbit, far from their stars, where glare is reduced. Only a few dozen exoplanets have been directly imaged so far, such as the planets of HR 8799. These images provide valuable data about atmospheres, compositions, and orbital paths. Future missions with larger telescopes and space-based optics promise sharper results, possibly including Earth-sized planets. Advanced optics remain essential to turning faint planetary glimmers into detailed observations, bridging the gap between indirect detection and true planetary portraits. Technology is improving rapidly, pushing the limits of exoplanet detection. Instruments now achieve precision once thought impossible, measuring stellar wobbles of just a few meters per second or brightness, dips of less than 1%. Space telescopes like Kepler, TESS, and JWST have expanded the reach of discovery, while planned missions such as the Nancy Grace Roman Space Telescope aim to take the next leap. Imagine the difference between looking through a small telescope in a backyard and a giant observatory with perfect optics. The detail revealed is transformative. Ground-based observatories also benefit from adaptive optics, making them capable of spotting planets directly. Advances in computing allow astronomers to filter noise, separate signals, and confirm candidates faster. Each step brings the discovery of smaller, more Earth-like planets closer to reality. The pace of progress suggests that within decades, scientists may be able to study exoplanet atmospheres routinely and even capture direct images of habitable worlds. Technology continues to turn distant dreams into observable science, driving the rapid growth of exoplanet research. The James Webb Space Telescope, JWST, is revolutionizing exoplanet science with its powerful infrared instruments. It can capture the faint light from planets and separate it into spectra, revealing details about atmospheric composition. For example, JWST has already studied gas giants and smaller rocky planets, detecting carbon dioxide, water vapor, and hints of other molecules. Imagine watching a planet transit its star and being able to read the gases in its sky from light alone. JWST's sensitivity makes it possible to study cooler planets, including some in habitable zones, something earlier telescopes could not achieve. It also provides temperature maps, cloud structures, and data on how heat moves around planets. Each observation refines models of planetary climates and chemistry. JWST is not only confirming what scientists suspected, but also surprising them with unexpected atmospheric signatures. Its findings help answer questions about how planets form, evolve, and maintain stability. For exoplanet science, JWST represents a leap forward, transforming faint signals into detailed profiles and pushing the search for habitable worlds and potential biosignatures closer to reality. The European Space Agency's Ariel mission, scheduled for launch in the 2030s, will focus on studying exoplanet atmospheres. Unlike general-purpose observatories, Ariel is designed specifically for this task. It will survey hundreds of planets, from hot Jupiters to smaller rocky worlds, using spectroscopy to measure atmospheric gases, temperatures, and clouds. Imagine a mission built to act like a planetary weather satellite, except aimed at dozens of distant worlds at once. Ariel will create a uniform dataset, allowing scientists to compare atmospheres systematically rather than piecemeal. This will help answer broad questions about how planets form and why they are so diverse. By examining different star types and planetary environments, Ariel will also explore how stellar radiation shapes atmospheres. The mission's scale ensures a clearer statistical picture, moving beyond isolated case studies. Ariel represents a major step in coordinated exoplanet research, providing the first large survey focused on atmospheric properties. Its results will complement JWST and ground-based telescopes, giving context to detailed studies by building a broader framework of knowledge about planetary climates. Plato, another European Space Agency mission, will search for Earth-like planets when it launches in the 2020s. Unlike Ariel, which targets atmospheres, Plato will focus on detecting and characterizing planets in habitable zones. It uses the transit method, monitoring large areas of the sky for long periods to capture brightness dips caused by planets crossing their stars. Imagine a telescope watching millions of stars like a surveyor, catching the faint flickers that betray Earth-sized worlds. Plato will also study host stars in detail, measuring their ages, masses, and activity levels. This helps determine whether planets are truly Earth-like or just similar in size. By focusing on bright nearby stars, Plato ensures that the planets it finds can be studied further by other missions. Its combination of planetary discovery and stellar science makes it unique, promising breakthroughs in identifying habitable zone planets around Sunday. Like stars, Plato's discoveries will be key targets for JWST aerial and future instruments, guiding the next stage of the search for life. Ground-based telescopes like the Extremely Large Telescope, ELT, will play a major role in exoplanet science. Currently under construction in Chile, the ELT will have a mirror nearly 40 meters wide, making it the largest optical telescope ever built. Its size gives it extraordinary resolution, allowing it to directly image exoplanets and study their atmospheres. Imagine standing on a mountain and peering through a telescope powerful enough to separate the light of a planet from its star across light years. Adaptive optics will correct for atmospheric distortion, producing sharper images than ever before. The ELT will complement space missions by observing planets discovered by TESS, Plato, and others, providing follow-up data on mass, orbit, and atmosphere. It may even be able to detect biosignatures in nearby habitable zone planets. Other giant ground-based projects, such as the 30-meter telescope and the Giant Magellan Telescope, will add further capabilities. Together, these observatories mark a new era, where Earth-based instruments rival or exceed some space missions in exoplanet research. Exoplanet catalogues expand every year as new discoveries are confirmed. From the first few in the 1990s, the count has grown to more than 5,600 confirmed by 2025, with thousands of candidates awaiting confirmation. Each year adds not only numbers, but also diversity, with new types of worlds identified, from ultra-hot Jupiters to small rocky planets. Imagine a steadily growing library, each new entry describing a world with its own orbit, size, and composition. Catalogues are important because they allow scientists to see patterns across populations, identifying common planet sizes and orbital arrangements. They also help refine estimates of how frequent habitable zone planets may be. Missions like Kepler, TESS, and radial velocity surveys continue to contribute, while future observatories promise to accelerate discoveries. Catalogues are living records of exploration, with each edition expanding our knowledge of planetary diversity. They also guide research priorities, pointing telescopes to the most interesting targets for atmospheric or habitability studies. The growth of these catalogues reflects both technological progress and the abundance of planets in the galaxy. Artificial intelligence (AI) is becoming essential in exoplanet science, helping sift through massive datasets. Missions like Kepler and TESS produce thousands of light curves, each containing subtle dips that may signal planets. Sorting real signals from noise requires time and precision. AI algorithms can scan these datasets far faster than humans, identifying likely candidates for further study. Imagine a digital assistant trained to recognize the faint fingerprints of planets across millions of stars, flagging those worth a closer look. AI has already confirmed exoplanets missed in earlier analyses, proving its value. It can also model complex systems, separating overlapping signals from multiple planets, or filtering out stellar activity. Beyond detection, AI assists in predicting planetary properties and simulating formation histories. By automating tedious tasks, AI frees astronomers to focus on interpretation and follow-up. The partnership between human expertise and machine learning is accelerating discoveries, ensuring that the flood of data from modern telescopes can be turned into meaningful science. AI is now a key tool in expanding and understanding the exoplanet catalogue. Citizen scientists contribute to exoplanet discoveries by analyzing data from missions like Kepler and TESS. Programs such as Planet Hunters allow volunteers to inspect light curves for transit signals. Human eyes can sometimes spot patterns that algorithms miss, especially irregular or complex ones. Imagine thousands of people worldwide checking graphs of starlight, each marking potential dips that may point to new worlds. Several confirmed exoplanets have been found this way, with citizen scientists listed as co-authors on scientific papers. Their contributions not only expand the pool of discoveries, but also engage the public directly in research. Citizen science projects make astronomy accessible, turning vast datasets into opportunities for collaboration. They also help train AI systems, since human classifications provide examples for algorithms to learn from. The combined effort of professionals, machines, and volunteers creates a powerful system for discovery. Citizen scientists show that planetary exploration is not limited to observatories or laboratories, but can involve anyone with curiosity and patience. Their role ensures that the search for worlds remains a shared human endeavor. Citizen scientists contribute to exoplanet discoveries by analyzing data from missions like Kepler and TESS. Programs such as Planet Hunters allow volunteers to inspect light curves for transit signals. Human eyes can sometimes spot patterns that algorithms miss, especially irregular or complex ones. Imagine thousands of people worldwide checking graphs of starlight, each marking potential dips that may point to new worlds. Several confirmed exoplanets have been found this way, with citizen scientists listed as co-authors on scientific papers. Their contributions not only expand the pool of discoveries, but also engage the public directly in research. Citizen science projects make astronomy accessible, turning vast datasets into opportunities for collaboration. They also help train AI systems, since human classifications provide examples for algorithms to learn from. The combined effort of professionals, machines, and volunteers creates a powerful system for discovery. Citizen scientists show that planetary exploration is not limited to observatories or laboratories, but can involve anyone with curiosity and patience. Their role ensures that the search for worlds remains a shared human endeavor. The ultimate goal of exoplanet science is detecting signs of life. Scientists search for biosignatures, chemical patterns in atmospheres that indicate biological activity on Earth. Oxygen and methane coexist because life replenishes them. Finding similar imbalances elsewhere would be a strong clue. Imagine observing a planet and discovering spectral fingerprints of oxygen, carbon dioxide, and methane in just the right proportions. While geology can mimic some signals, combinations unlikely without biology would be powerful evidence. Telescopes like JWST and future missions aim to detect these gases on rocky planets in habitable zones. Even microbial life would transform our understanding of the universe, proving that biology is not unique to Earth. The search focuses not only on Earth, like planets, but also on moons and water worlds, where alternative forms of habitability may exist. Discovering life elsewhere would answer one of humanity's deepest questions: are we alone? This quest drives much of exoplanet research, shaping the design of missions, instruments, and observational strategies. Exoplanet science is one of the fastest growing fields in astronomy. In just 3 decades, it has moved from the first confirmed discovery to thousands of known planets and detailed studies of their atmospheres. Each new mission expands the range of discoveries, from hot Jupiters to Earth-sized worlds. Imagine an area of science where every year brings dozens of new findings, reshaping theories about how planets form and evolve. Advances in technology from space telescopes to ground-based observatories fuel the pace of progress. The field is also highly interdisciplinary, linking astronomy, geology, chemistry, and biology. This attracts scientists from multiple backgrounds, broadening approaches and insights. Public interest adds momentum as exoplanets capture imagination and inspire questions about life in the universe. With missions planned for the coming decades, exoplanet science is set to grow even faster. It is no longer just about discovering planets, but about characterizing them, studying atmospheres, and searching for life. The rapid rise of this field shows how curiosity and technology combine to drive exploration on a cosmic scale.